Hi, I'm Yael, and in this talk I will present general compilers in the CONGEST model, which obtain resilience against adversarial edges. And this is a joint work with Merav Parter. So one of the common models in distributed computing is the CONGEST model, where we model the network as an undirected graph with n vertices. Every vertex has a unique identifier of log and many bits, and at the beginning of the computation, every vertex only has a local view of the network. So every vertex only knows its incident edges. Then the network proceeds in synchronous rounds, where in each round, each vertex can send at most log and many bits over each one of the edges. So we have bandwidth limitations. And the main complexity measure that we usually look at is the round complexity, the number of rounds it takes us to solve the problem. Now let's assume that I have some evil adversary that controls some of the vertices or the edges in my graph. I would like my algorithm to still be resilient to this kind of attack, and all the vertices, all the correct vertices, to still be able to compute the correct output. And the key question that we ask is, what is the cost in terms of number of rounds for designing algorithms in the CONGEST model that are also resilient to adversarial attacks? We extended the CONGEST model to the adversarial setting. We call it the adversarial CONGEST model, where additionally we have some Byzantine adversary that controls a fixed set of the vertices or the edges, and this set is unknown to the rest of the vertices. And my adversary has unbounded power. It knows the graph, all the internal randomness, and all the messages that are exchanged throughout the algorithm. And then this adversary can drop messages or send corrupted messages in every round. And the communication proceeds just like in the CONGEST model, where in this talk, I will also assume that the vertices hold a polynomial estimate on n, the number of vertices, and a linear estimate of the diameter, which we denote by d. Now, currently, most of the algorithm in this adversarial setting, usually they assume that the communication graph is complete, is a clip. As for general graphs, Dolev showed that in order to obtain resilience against f adversarial edges or vertices, I need my graph to be at least 2f+1 edge or vertex connected. So from now on, I will only talk about graphs that are 2f+1 connected. Okay, so in this work, we designed a general compiler that translates any algorithm A that is designed for the CONGEST fault-free setting into an equivalent algorithm A prime that performs the same computation, but in the presence of adversarial edges. Now, note that in general, we can't obtain such general compilers for adversarial vertices. So here we just focus on the edge case. Now, the compiler works in a round-by-round manner. And so if we look at some round J of algorithm A, and let's look at some vertex V and all the messages that it received in algorithm A in round J. Then in algorithm A prime, I require that V will still receive the same set of messages and also ignore all the corrupted messages that were initiated by the adversary. And the main complexity measure of our compiler is the round overhead of compiling each round. Recently, Parter and Yogev studied general compilers for CONGEST algorithms in several adversarial settings. And the key tool that they used, they called it low congestion cycle cover. So what is a cycle cover? Given parameters C and D, a CD cycle cover is a collection of cycles such that every edge E is covered by some cycle, meaning there exists a cycle that contains this edge. Additionally, every edge appears on at most C cycles. This is called the congestion. And every cycle has length at most D. This is called the dilation. Now, intuitively, if I have a cycle cover, then this provides me two edge disjoint paths for exchanging messages. So if I have just one adversarial edge, I can still exchange messages between the two endpoints through a reliable path. Now, Parter and Yogev also showed that if I have a bridgeless graph, there exists a deterministic algorithm that works in the CONGEST fault-free setting for designing a cycle cover with congestion C, O hat of 1, and dilation and round complexity O hat of D, where this O hat, it hides factor of the form 2 to the power of square root log n. Okay, now using these cycle covers, they constructed general compilers against a single adversarial edge with round overhead O hat d to the 5. And here in their compiler, they assumed that the cycle cover is computed in a fault-free pre-processing step. So first they compute the cycle cover in the fault-free setting, and then they use it in the compiler. In our work, we extended the compilers of Porter and Yogev, and first we designed compilers that also handles multiple edge faults. And this also results in an improved compiler for the single fault case with round overhead of O hat d to the cube. And the main contribution of our work is that we omit the fault-free pre-processing step, meaning that all the computation is computed in the adversarial congest model, where we have adversarial edges. And in order to handle multiple faults, we extended the notion of low congestion cycle cover, and we introduced fault-tolerant cycle cover. So given a parameter f, an f fault-tolerant cycle cover is also a collection of cycles. And here, for every edge E and every edge set E prime of size at most 2f minus 1, there exists some cycle C that covers the edge E that contains E and also avoids all the edges in E prime. Now note that I don't require that all the cycles covering some edge, I don't require that there will be disjoint. Now intuitively, if I have an F fault tolerant cycle cover, then for every F adversarial edges, for every other edge E is still covered by a collection of cycles that does not contain any adversarial edge and with large flow, with flow at least F. Okay, so why this is good for us? So given that I have an F fault tolerant cycle cover, then the high level idea of the compiler is as follows. Let's look at some round J of algorithm A and look at a message that some vertex U sent its neighbor V during algorithm A. Then in algorithm A prime, U is going to send V the same message over the edge UV and also over all the cycles that cover this edge. Then V is going to decide which message is the correct message that you send by accepting a message as the output only if it received this message over a path collection with large flow, with flow at least F plus 1. And why does this work? So let's say I have some evil corrupted message M that was initiated by the adversary. I know that every path that passed this message must contain at least one adversarial edge. So if I look at the path collection that propagated this message to V, it has flow at most F. Now, on the other hand, in my F fault tolerant cycle cover, the edge UV is covered by a path collection or by a cycle collection of reliable cycles that does not contain the adversarial edge with large flow, with flow at least F plus 1 if we also include the edge UV. So for the correct message that V sent, indeed V is going to receive it over a path collection with large flow. So we can distinguish between the correct message and the corrupted messages that were initiated by the adversary. In general, we showed that given that I have an F fault tolerant cycle cover with parameters C and D, I can compile any distributed algorithm A in the congest model into an equivalent algorithm A prime that is resilient against F adversarial edges, and the round overhead is C times D to the cube. Then for the special case of a single edge fault, we can do a little bit better. And we show that if I have a one fault tolerant cycle cover with parameters CD, then I can compile the algorithm A to an algorithm A prime that is resilient against a single adversarial edge with round overhead of CD square. Okay, then our main results are constructing the fault tolerant cycle cover in the adversarial congest model, where we also have adversarial edges. So for the single edge case, we showed that if I have a 3-edge connected graph with one fixed adversarial edge, then we have a deterministic algorithm for computing one fault tolerant cycle cover with congestion C O hat D square dilation O hat D, and round complexity O hat D to the 4. Then we also showed improved randomized algorithms with congestion and dilations O hat of D, and round complexity O hat D square. So if we combine our randomized construction for one fault-tolerant cycle cover together with a general compiler for this case, then we get a compiler with round overhead O hat D to the cube. Okay, so for multiple edges, we showed that if I have two f+1 edge-connected graph with f unknown adversarial edges, then we have a deterministic algorithm for computing an f fault-tolerant cycle cover with dilation D O hat fd and congestion and round complexity O hat df log n to the power of f, where I added this asterisk to the fault-tolerant cycle cover because for technical reasons, we don't really compute a fault-tolerant cycle cover, but we compute a collection of cycles and also paths that contains a fault-tolerant cycle cover. But for the application of our compiler, this is enough. Okay, so we showed a construction for a fault-tolerant cycle cover, and we have this exponential dependency in F. And then we asked, is this exponential dependency essential? And we answered this question in the affirmative, and we showed that for every parameters f and d, there exists some 2f+1 edge-connected graph with diameter d, for which every f fault-tolerant cycle cover with parameters c and d, the congestion plus dilation must be exponential in f. So the congestion plus dilation is at least d over f to the power of f. In this quantity, C plus D, we also call it the quality of the cycle cover. Okay, so I will now elaborate on the construction of one fault-tolerant cycle cover, and this serves as a building block for the general fault-tolerant cycle covers. Okay, the construction consists of 3 steps. First, we apply the fault-free cycle cover algorithm of Parterre and Yoger, but not on the graph G, and rather on a collection of subgraphs with special properties that we call a covering family. And I will explain in a few minutes what is exactly a covering family. And these subgraphs in the covering family, some of them might contain the adversarial edge. So some of the cycles that we compute in step 1, some of them might be totally corrupted. Therefore, in the second step of our algorithm, we apply a verification procedure on the cycles that we obtained in step 1 in order to verify which cycles are indeed legal cycles in G with the length and the congestion that we want. And the verification is done by propagating certain messages in both directions of every potential cycle. And this step is the most technical part of our algorithm because intuitively, because the adversarial edge, it might manipulate and corrupt also the verification messages. So we needed to handle this. Now the covering family that we use, it has some nice properties that guarantees us that after these first 2 steps, all the reliable non-adversarial edges are covered by good cycles, by reliable cycles. But for the purpose of our compiler, it is important for us to also cover the adversarial edge with good cycles. So in the third step of the algorithm, we cover the remaining adversarial edge if we need to. And this is done using the essential cycle that is obtained by a BFS tree in G without E prime, without the adversarial edge. Okay, now note that because of the verification step, if the adversarial edge is indeed not covered in the first 2 steps, the endpoints of the adversarial edges are going to know about it, okay? So it can't be the case that the endpoint of the adversarial edge think it is covered, but it is not covered. This is guaranteed by the verification step, and this is one of the reasons it was important to us. Okay, so this was a high-level idea of the construction, and I will now explain what is a covering family. So a covering family is an ordered family of subgraphs where for every pair of edges, E and E prime, there exists some subgraph Gi that contains E, does not contain E star, and also contain a short cycle of length order D that covers the edge E, between the endpoints of the edge E. So given a covering family, we have the guarantee that for every reliable non-adversarial edge E, there exists some good subgraph GI that contains E, also contains a short cycle that covers E, and also GI does not contain the adversarial edge. So all the edges in GI are reliable, and when we apply the cycle cover algorithm of Parterre and Yogev on GI in the first step of the algorithm, then the edge E is going to be covered by a good cycle. Now, because the vertices doesn't know the topology of Z, we don't expect them to actually learn exactly the subgraph in the covering family. So instead, we require that the vertices only locally know the subgraph family, in the sense that every vertex U can determine for each one of the incident edges to which of the subgraphs it belongs to. Recently, Kartik and Parterre showed that if I have a 3-edge connected graph, I can compute a covering family for this graph of size O tilde D square, where D is the diameter, which is locally known. And I can do this in 0 rounds, meaning without using any communication. Okay, and I'd just like to know that here in this algorithm, this is where we needed the assumptions that the vertices hold an estimate on n, the number of vertices, as well as on the graph diameters. Okay, so in the remaining time, I would like to talk about the fault-tolerant cycle cover lower bound. Recall that if I have an F fault-tolerant cycle cover, so I'm given a collection of cycles where for every edge E and an edge set E prime of size at most 2F minus 1, there exists some cycle that contains E and avoids all the edges in E prime. So if I look at the path collection that is induced by all the cycles that covers some specific edge E, then this is a collection of paths between the endpoints of this edge E, and it also has large flow. It has flow at least 2F. Then in order to prove the lower bound for fault-tolerant cycle covers, what we do is we provide a graph theoretical characterization of route sets which also have large flow, where a route set for 2 vertices is simply a collection of UV paths. So if I have 2 vertices U and V, this is simply a collection of paths. And in our key theorem, what we show is that there exists some graph G, which is 2F plus 1 edge connected with diameter D, and it also contains some edge UV, such that every route set of U and V with large flow, with flow at least 2F, then either the route set contains a path which is very long, path of length D over F to the power of F, or there exists some edge that lies on at least D over F to the power of F many paths. Okay, now because every F fault-tolerant cycle cover for this graph G, it induces a UV route set with large flow, it will then follow that any F fault-tolerant cycle cover for G has a quantity congestion plus dilation, which is at least D over F to the power of F. Okay, so the quality is at least exponential in F. And how does this graph G look like? So it contains 2 F layers. Well, in the first layer, we simply add a path between U and V of length order D. Then in every layer that we add a D length path that covers each one of the edges that we added in the previous layer. So this is how the second layer will look like, and this is how the third layer looks like. And in order to maintain large edge connectivity in the last layer, in layer 2F, we simply replace every vertex by a click, and every edge is replaced by a matching between the corresponding clicks. And additionally, we also add the edge UV to the graph. Now, for every route set of U and V with large flow, I know that for every edge set E prime of size at most 2F minus 1, there exists some path in the route set that avoids all the edges. And the key argument that we use in order to show the lower bound for UV route set is that we showed there exist exponential many edge sets such that every path in the route sets that avoids X many sets has length at least X times D. Okay, so we show a trade-off between the number of paths and the length. So this basically means that if in my route set it has small dilation, all the path is short, then there must be many paths, and therefore there exists some edge with large congestion. So to sum things up, in this work we presented general compilers that translate any congest algorithm into an equivalent algorithm that is also resilient against adversarial edges. To do so, we used a new notion of fault-tolerant cycle covers, which extends low congestion cycle covers, and we also gave algorithms for computing them in the adversarial setting when we have adversarial edges. Finally, we also gave a lower bound for the quality of fault-tolerant cycle cover, which is exponential in F, the number of faults, and we do so using a combinatorial lower bound for route sets with large flow. Thank you for listening.